for both, actually for both cables and arches, we solved when they were acted upon by UDL and point load. And also we discussed some aspects of influence line diagram before the midterm. So in that we plotted influence line diagram by using simple shear force and bending moment diagram. I hope you have revised this concept again. And the other methods that we used was tabulating, plotting the, yes.
Sir,
Yes.
ये lecture kindly आप recording पे डाल दें.
Okay. Thank you for reminding me, by the way. It is in the recording. I think it is in the recording mode already.
सर वो किधर कर रहे हैं?
So we plotted ILDs by tabulating values and using equations. And the first thing that we are going to study after midterm is the plotting of ILDs by using the Muller's principle. And after that, we will be discussing how to interpret or calculate maximum shear force and bending moment when the moving load is moving over any structure. These may include pin connective structures as well, such as trusses or girder. So basically, up till now, we have been plotting the influence line diagram for the beams only, but we will move on to the trusses as well. And the next major topic is the deflection and rotation in the structure, for which we will be using. Someone's mic is turned on, so I suggest him to turn it off. So the next, in the rotation and deflection, we'll be studying method of integration or double integration, moment area, conjugate beam, virtual work method, and Castigliano's theorem. So this is the content that we will be covering after midterm. So it doesn't look too much, and I hope it will be easy for you. And the reference materials, the first and most important thing is obviously, again, the class lectures. You know, everything we discuss in the class, and sometimes we study or understand the concept in a different way as mentioned in the book. But again, book is always the book has the final say. So the book that we are following is the Structural Analysis by R.C. Muller. And most of you already have this book, and those who don't will get the access through HEC library, which I think GIK would have provided you with up till now, or maybe they will provide you very soon. So before moving on to the lecture, I would like to review briefly what we have studied about the influence line diagram pre-midterm. So what is ILD basically? It is basically the representation of variation of a function. Now by function, whenever I use this term, you should understand that it will mean the shear force, bending moment, or reaction, all three together. So ILD basically represents the variation of a function at a particular point as the unit load moves along the structure. So what does this mean? If, for example, we have this beam and I want to plot the ILD for shear force at C point. Where is my C point? This one, right? So if I want to plot the influence line diagram for this point, I will move this unit load throughout the length of this beam. For example, I will move it like this. First, I will place it over here and calculate the shear force at this point by our simple bending moment diagram or shear force diagram. And I will plot this point over here, right? So if my unit load is at 12-meter distance from A spot, this is the value of shear force at point C. So similarly, I will move the unit load, let's say at this point, and I will calculate the shear force again at this point C by simply applying the laws of mechanics or the bending moment diagram, and I will plot it over here. So basically at this point, the shear force is 0. So this is this value, or this is the representation. Similarly, if I want to plot the ILDs for the bending moment at point C, I will do the same thing. I will move the point load or the unit load over the entire length of the beam, and we'll calculate the value of bending moment at this point, and I will represent this graphically. And for the reaction, it's the same thing. If you want to plot, for example, this diagram is for the vertical reaction at support B. So I will place the unit load, for example, let's say first at this point, and I will calculate the reaction RB, and then I will plot it on the graphic. I will represent it graphically. So this value of 2 means that when my load is at this point, the reaction value or the reaction is 2. And this value, similarly, when the load is, let's say, at this point, the value of reaction is 1 over 5x or whatever is the value. We can calculate it by simply applying the laws of equilibrium. And some of the conclusion that we made through this, after studying this ILD, was that the ILD for shear force and bending moment, in any case, in any type of beam, for example, let's say if it's an overhanging beam or a simply supported beam, it will always pass through the support. What does this mean? This basically means that when I plot the ILD for point C using this unit load, or basically ILD is for the unit load only, then at the support, the value of the shear force will always be 0. For example, you can see in this figure, and this will be valid for any type of structure. Similarly, as you can see for the bending moment, the value of ILD at both the supports is 0, right? And another important conclusion was there is no first degree or second degree curves, just as we used to have in the case of shear force and bending moment for these ILD. ILDs will always be in the triangular shape. And the benefit of such kind of shape is that if you know one value, you can calculate all the other ordinates or the values by using the concept of similar triangles or by simple mathematics. And the third point is that for the shear force, at the point or for the point for which we are constructing the ILD, the absolute sum will be equal to 1. For example, in this beam, we were developing the influence line diagram for shear force at point C. And you can see in this figure that the absolute sum of these two values is equal to 1. For example, it is 0.5 and this one is also 0.5. And this conclusion is also valid for all types of structures, any type of beam. First, there will be an abrupt change at the point under observation or under consideration, and absolute sum of the values will always be equal to 1. But in the case of bending moment or the ILD for bending moment, although the absolute sum is not equal to 1 at the point for which we are developing the ILD, but it will be maximum. So 1 is like an absolute value, but maximum can be any one. It can be 0.5, but one thing is for sure that it will be maximum of the entire length. Okay, so you should remember this difference. And for the support reaction, as you can see in this one also, that for the support for which we are developing the ILD, for example, in this figure we were constructing the ILD for reaction at B point. The value of ILD at B, for example, this value will always be equal to 1. Okay. Or if I was developing the ILD for the reaction at A, it would be something like this. But this value would be equal to 1. Okay. So this is true for all types of supports. That for the support for which you are developing the ILD, the value would be equal to 1. And for the other support, for example, in this question, I was developing ILD for B, the ordinate is 1, and the other support is A. And for that support, the value of ILD will always be equal to 0. And this will also be true in all the cases. So these are some important conclusions that we have developed for the ILDs. And if you have any questions about the ILD, you can ask me right now. And after that, we'll move on to the next topic. So I think you understand the concept quite well now. Previously, we were developing the influence line diagrams for by using the method of tabulation or by using the equation for the ILDs. But now we will move on to plot the qualitative ILD. What does qualitative ILD means actually? It means that we won't have to use the traditional method or the method of using the equation, plotting the shear force diagram, and then doing the ILD. In this method, which was proposed by Muller in 1886, he gave us an alternative method by using which we can plot the shape of ILD by simply looking at the beam. He basically stated that the shape of ILD is equal to the deflected shape of the beam when the beam is acted upon by that function. Now the function, you know what is function means. So let me show you this on the whiteboard, that what does this concept mean. For example, let's say I have this beam, simply spotted beam with a hinge on one side and the roller on the other side. And I want to plot the ILD for reaction at A. This is my A point and this is my B point. Can anyone confirm me that it's visual and you can understand it?
Yes, sir. We can see it.
Okay. So this is my simply spotted beam, and if I want to plot the ILD for reaction at A, what do I need to do? Actually, Muller said that the deflection of this beam is equal to ILD. Or the deflection, I mean the deflected shape. Okay. So if I want to plot the ILD for RA, what do I need to do? I simply have to remove this support. Let's say I will plot it again. This support will remain as it is. I will simply remove this support and apply a vertical reaction at this point. Okay. And plot. And now when I apply the vertical reaction at this point, how will the beam deflect? It will deflect something like this. Now this is the deflected shape. And Muller said that this deflected shape is equal to the ILD shape. Now, when you plot the ILD for this beam using our, or let's say if this is the 4-meter length, and you plot the ILD by moving the unit load as we used to do in the previous concepts that we have learned, you will also get this similar kind of the shape. And Muller said that we need to remove the capacity of the beam to resist that function. What does this statement mean? It actually means that if I want to plot the ILD for reaction, I would assume that the beam cannot resist that reaction. And this is what I did in this question. I removed this support and applied this reaction. So that means that the beam cannot resist this reaction and it will deflect. And how will it deflect? It will move something like this. And this deflected shape is equal to ILD. Similarly, if I want to plot the ILD for shear force at, let's say, C point. So what will I do? The first thing I need to do, I have to assume that the beam cannot resist the shear force at point C. So at this C point, the beam cannot resist, and I would apply the shear force from myself. How will the shear force act? Something like this. If I cut the beam into two sections. Now let's say I will plot this beam into two parts. I will cut the beam into two parts or two sections, and I will apply shear force at this section. Shear force acts something like this. These are two opposite and equal forces acting on the face of the structure. Now, in this case, how will the beam deflect? When you apply the load at this point, this part will move something like this, and this part will move upwards, right? So if I combine these two parts, so the shape that I have plotted is basically the deflected shape, and it is equal to the ILD, right? So you have to, it's just like a game. You have to remove the capacity of the beam to resist that particular function and plot the deflected shape, which will be equal to your ILD.
सर आपने इसी डायरेक्शन में क्यों बनाई है?
Just,
shear
this
force की वो.
Okay, actually, I will tell you in the next slide. So basically, this is our sign convention. I would have plotted in this direction as well, but obviously we need to have one unified convention for all the cases. So we will make it a compulsory thing that always on the left side it will act downward and on the right side it will act upward, right? There is no major concept behind this, because this is a, you can say, a statistical or based on some assumptions. And if I need to plot the ILD for bending moment at point C, again, I will divide the beam into two sections, this one and this one at point C. This is my point C, and I will apply, a beam cannot resist the bending moment. So I will apply two opposite bending moments at this point, and I will again check or see how will the beam deflect. So when I apply the counterclockwise, or if I hold this point and try to rotate the beam, what will happen? This part will move up like this, and this part will also move up something like this. So do you think that this is the shape for our ILD? I have shown you in the slide also. This was the shape of our ILD by using this tabulation method or by the method of equation. So this is what the concept of ILD by using the Muller principle means. Muller principle means, okay. Now, obviously, there will be some basis of this concept, that how did Muller came to this conclusion or this concept. So basically, it was based on the visual work method. The method actually states that the work, as we all know, that the work is the product of linear displacement and force in the direction of displacement, or the rotational displacement and movement in the direction of displacement. And for the body to be equilibrium, the work done by all the forces and movement should be equal to zero. Actually, Muller used these two principles to propose this method. So what does this principle basically means? Let's say I have a beam or a simply supported beam. This is the visual work principle that Muller used. Let's say if I have a simply supported beam, just ignore this diagram, and I want to plot the ILD, or how Muller actually did. And as I shown you before, that if I want to plot the ILD for reaction at A support, what I did was I removed this support, or considered that the beam cannot resist this vertical reaction, and plotted the deflected shape. Now, what does this deflected shape look like? It looks like something like this. And what is this? Can I say that this is the deflection at A point? And at this point, for example, what is ILD? ILD is basically as the unit load moves along the length, we calculate the reaction. So let's say our unit load was at this point when we plot at this point, and we calculated the reaction. And due to this unit load, or due to this deflection, let's say at this point our deflection is delta y dash, or we can name it as anything. So if this body needs to be in equilibrium, or if this beam is to be in equilibrium, the work done by both these forces should be equal to each other. Now, what is work done? Work done is basically the force multiplied by displacement. So can I write it like this? That the work done due to this force is equal to RA delta A minus, because it is acting on the opposite direction. So due to this unit load, or due to this force, we have this deflection. Actually, it is not due to this unit load. It is basically due to this load. But since it is acting under this unit load, So this load will try to resist this deflection. So it is basically doing some kind of a work in producing the deflection in the opposite direction. So the sum should be equal to 0 for the whole body to be in equilibrium. So that means if I take this term to the other side, I will get this equation. So let's say that the deflection that we gave to this beam is equal to 1. So the deflection is equal to 1. Then I will get RA is equal to delta y dash. Delta y dash. Okay, so I get this direction.
सर ये मुझे
Sir-
समझ आया कि रेजिस्ट वाला आपने जो बताया कि ये रेजिस्ट कैसे करे, ये तो एक ही डायरेक्शन के अंदर है.
What do you mean by one direction?
सही मतलब कि ये तो डिक्रीजिंग उसके अंदर ही जा रहा है, जो डेल्टा ए और वो जो 1 वाली.
No, look, what is this load doing?
अच्छा,
This load is trying to move this upward, this beam. And what is this load doing? It is trying to move in the downward direction. So the work done, this will be, if I take this one as positive, this one should be negative, right?
Yes, sir.
So this is what I did simply.
Okay.
Okay. So now I have this equation or this conclusion from this one. Now what does this conclusion physically mean? It means, yes.
सर ये वर्क डन वाला एक दफा दोबारा रिपीट कर दें.
Actually, the idea is that Muller would have used some kind of concept to give us this idea that you can plot the deflected shape and you can say that it is equal to ILD. So we are basically discussing that concept. He uses the concept of virtual work. Actually, work done is simply the product of applied force and the displacement. And Muller said that, or in the case of ILDs, what we used to do by using the method of Muller is that we applied the reaction at a particular point and we plot the deflected shape of the beam, right? Just like this. So when I applied the reaction at this point, the beam will deflect, as I have shown you in this red point with this red pointer. The beam will deflect something like this, and it will produce the deflection delta A at this point. And let's say that the deflection at this point is delta y dash when our unit load was at this point. Let's say I call this point as C. So what is work done? Work is simply the product of force and displacement. So what is my force at this point? It is basically RA into delta A. And what is my work done at this point? 1 into delta Y. And why these are in the opposite direction? Because this force is basically trying to push this beam in the upward direction, and this force is trying to push this beam in the downward direction. So they both are actually opposite to each other, or acting in the opposite direction to each other. So I simply write the equation of equilibrium for this beam, and the equation will be something like this, and I move this part to the other one, and I get this. Now let's say that the deflection that we gave to this beam was equal to 1, then what will our equation looks like? It will be something RA is equal to delta Y dash. So you got the idea, right?
सर
Yes.
जब हम वहाँ पर पॉइंट ए पर हम अप्लाई कर रहे थे ये यूनिट लोड, तो सर तभी डायरेक्शन मतलब ऐसी बन रही थी शेप. अब हम सी पे अप्लाई कर रहे हैं तो फिर भी शेप ऐसे बन रही है.
No. Actually, we are not applying on C. Basically, at C, there is a unit load that is always acting. For example, what is our ILD? ILD is like that my point load is moving throughout the length of this beam. Okay. So, for example, I can also say that the one can be at this point. I can also say that one can be at this point. So basically, this means that when the unit load was at this point, then my deflection would have been this one, delta Y dash, right? And that's what I'm saying, that we applied RA only. We didn't apply 1. 1 is already on the beam, and it is at every point at one moment. Got it?
Yes, sir.
Okay. So I got this equation. Now, what does this equation mean? This means that the value of reaction when I plotted the deflected shape, the value of reaction at this point is equal to the deflection at this point. So can anyone tell me what does this physically means? And how can you relate it with the concept of ILDs, this equation? Anyone? Is that no?
सर रिएक्शन पे रिएक्शन एक पॉइंट पे रिएक्शन अप्लाई हो रही है जो which would be equivalent to the change of force at y position, c position, sorry.
Not the change of force, basically it is basically the deflection at this point. Okay, yes, the reaction at a point. And what is the ILD? For example, if my ILD for this beam is like this, what is this component? This component, if I plot the ILD for reaction at a point, what is this component? Anyone?
RA.
This is RA, right? So this component is basically RA, and this is what the Muller concept says, that RA is equal to delta Y. So basically the Muller came at this point through the path of deflection, and previously we were simply doing by the method of tabulation, right? So everyone got this concept. If there is no question, I assume that everyone has got the idea.
सर हम डेल्टा ए तो हम लोग एज्यूम कर रहे हैं ना कि इक्वल्स टू 1 है, तभी आर ए जो है वो डेल्टा वाई की इक्वल है.
Exactly.
तो हम हमेशा डेल्टा ए को हम लोग 1 ही कंसिडर करेंगे.
Actually, you can also assume delta A is 100, or maybe let's say any value. But again, in that case, it will be 25 RA. So it is this delta Y will be some kind of a magnitude, or will be equal to the let's say the product of some constant value with the reaction. So obviously there is a term of reaction in every case. So in this case, we are doing for the unit load. That's why we have taken it, or let's not call it like that. Or I can say you can assume at any value. For the understanding at this point, I have said that it is equal to 1. And for that case, you can say that we can equate the deflection and reaction, right? It can be any value. The idea is that the deflection is proportional to the reaction. So it depends on what type of deflection we gave at this point, and then it will be equal to the deflection at C point. Yeah.
Okay.
Now let's move on to the how actually the same concept apply for the case of shear force also. For example, if this is my beam, and as I've plotted above as well, and I want to plot the shear force for this point, this will be my shape. And this deflection, let's say I call it delta Y. And why is this deflection? Because I have a shear force that is acting at this C point, this shear force. And now in this case also, I would say that my unit load is acting at this point, and which is producing a deflection of delta Y dash. So the same concept will apply. I will multiply the what is work done, the product of force into displacement minus work done due to this unit load will be 1 into delta Y dash is equal to 0. So V delta Y is equal to delta Y dash. So again, if I take it is equal to 1, so my shear force will be equal to deflection. So again, it's the same principle as this one, that your shear force.
Sir?
Yes.
Sir, V is shear force at point C?
Yes.
Okay, sir. Thank you.
So in this case also, you can see that the shear force at this point is equal to the deflection, and this is basically our concept of ILD, that if I want to get the component of ILD at this point, it will be simply I will put on the unit load or UDL or point load at this point. I will calculate the shear force at this point, and this will be the component of ILD for shear force at this point. Now for the moment also.
सर ये बात फिर से रिपीट कर दें जो आपने अभी बताई है shear force की.
Okay. Actually, just like in the case of the reaction, for example, if I want to calculate the ILD for shear force at point C, I have to move the unit load throughout the length of the beam, right? So I will place, for example, my unit load is at this point now. So what will I do? I will place the unit load at this point. I will calculate the shear force at C, and when I will show it graphically, at this point, my component will basically the shear force at C point when the unit load is here, right? So this is what this concept employs. Yeah, you apply the shear force, you get the deflection, and this deflection is equal to the shear force value. And this is what we proved. You got it?
Yes, sir.
Okay. So in the case of movement also, the same principle of virtual work Muller applied. For example, if I want to get the value of ILD for movement, it will deflect something like this, as I have shown you in the above example as well. And there will be some kind of a rotation. So the work done in case of movement also states that the work done in case of movement is equal to the movement at that point multiplied by rotation, which we have got over this point, is equal to, what is this deflection? Let's call it as delta y dash due to unit load. So again, if we take it as 1, so our deflection under point load or unit load of 1 is equal to the moment load is equal to the moment at point C. And this is equivalent to the concept of ILD, just like in the previous two cases. So this was how Muller developed this concept. And basically, this is for your understanding. Let's move on to let's summarize the whole thing. So again, coming back to the topic, there are some steps to plot the qualitative ILD or ILD by using the method of Muller. It basically states that if we want to draw the ILD for support reaction, it is same as I have shown you in the example, in the first example that I have showed. That if we want to draw the ILD for support reaction, we should consider a roller guide at that support and get the deflected shape by applying an upward reaction. Now, this is what someone asked, that why we are taking only in the upward direction, or in the case of shear, why we are taking in the downward direction on the left side or the upward in the first side. So we basically make this as a convention. So this convention is the right one. If we take the other convention, that will give us the negative result. So it doesn't matter. So to draw the, let me show you on the whiteboard now. We'll be solving another problem. Let's say I have this beam and I have the support at this point and at this point. And I want to plot the ILD for shear force at point C. So let me solve another question first for the reaction, because we have been studying that concept. If I have this beam and I want to plot the influence line diagram for the reaction at point B. So what was our step? How many steps do we need to do? First, we need to remove this support. So the first step, we will remove this support and keep this support as it is. Let's say this is the ILD for RB. So I remove this support and apply a roller guide. Actually, this is just a representation. It doesn't imply anything. The roller guide basically means that the beam cannot resist the vertical force, but it can resist the horizontal forces if they act on the beam. So we will show a roller guide over there and apply an upward reaction equal to RB at this point, and just simply note down the plot the deflected shape. So this is my deflected shape, which is equal to ILD for RB. So this is
the
yes.
shape हर दफा बनाएंगे sir.
Eh?
ये डिफ्लेक्टेड शेप सर हर दफा बनाने जब भी हम लोग आईएलडी का क्वेश्चन सॉल्व कर रहे हैं, ये क्वेश्चन सॉल्व कर रहे होंगे।
Actually, this deflected shape is basically the ILD itself.
अच्छा
सर
This is
ये
what.
स्ट्रेट लाइन है या कर्व है?
Yes.
सर ये जो आपने ड्रॉ की है ये एग्जैक्टली स्ट्रेट लाइन है या ये कर्व में है?
Of
Bend
course,
है।
it's the straight line. Actually, I am
Right.
also learning this instrument, so give me this much space.
Sure, sir.
Okay. So these are the straight line, or assume that these are the straight lines. Okay, so
सर ये हम लोगों
yes.
ने बी पॉइंट तक नहीं बनाना था, तो लाइक हम उससे आगे क्यों लेकर गए? हम तो बी पॉइंट पे बना रहे थे ना, और हमने बी पॉइंट पे रिएक्शन लगाया
ILD for B point, right?
जी।
Actually, no. Obviously, we are plotting for the B point, but the ILD is for the whole beam. For example, if I give you the same question and if I ask you to plot the ILD, and the final answer you will give me this shape, right? This whole shape.
जी
So
सर।
what we need to do is we need to remove the support and note down the deflected shape of the whole beam. So when I apply the load at this point, just take a pen in your hand and apply a load, let's say at B point. What will happen? The beam will move upward direction as a whole, not just like this, not like this. Its deflection won't stop at this point. Just take a pen in your hand and apply a load at B point, and you will see that the whole pen will move up. It won't stop over here. So this is the whole deflected shape, and this will be equal to ILD, right?
Yes sir.
Okay.
Excuse me, sir.
Yes.
Sir, I wanted to ask. आपने पहले mention किया था कि for supports one value will be 1 and the other one will be 0. Reactions पे.
Yes.
तो अब इसमें क्या मतलब IB 1 होगा and the support that we have on the left वो वाली
This one?
value 0. Yes sir.
This. Yes, you got it right actually. Who are you, by the way?
Naveed sir.
Huh?
Naveed.
Naveed. Okay. Yeah, you got it right, and this is what we are going to do in our next step. But okay, this value is equal to 1 and this is 0, and now you can see that if by applying the concept of similar triangle, we can get this reaction, and simply by 3 or 4 steps, we got the ILD. We don't have to do the method of tabulation, method of equation. So that is why those concepts were important, or those conclusions were important. Okay. So if I want to plot the ILD for reaction at A, can anyone plot and show me the shape of ILD for A point? Anyone?
फिर RA पे reaction 1 हो जाएगा and middle पे 0 हो जाएगा.
That is the second thing. So we need to stick to the first one. We need to remove that support, apply the load at RA, and plot the deflected shape. So what will the deflected shape look like? Just don't think about any concept. Just apply the physical phenomena. Just consider that this is a pen which is supported at this point, and you are applying a force at this A point. So how will the deflected shape look like? Anyone?
सर सेम ही होगी, जस्ट ए पे
Triangle different हो जाएगा बस direction.
Like this one?
यस.
Do you think
B
so?
पे 0 होगा I guess.
सर बी पे 0 होगा सर.
Why?
बी पे 0 होगा सर, क्योंकि सर सपोर्ट पे रिएक्शन 0 होता है.
Okay, that is a concept that the reaction at support is 0, but that is the other thing that will come after this one. First, I am just asking you that apply the load at this reaction and just tell me, because this concept will apply for all the cases, but what if I have a simple beam with one support? Then you have to consider it physically. So don't go into that one right now. Just look at this beam physically, that you are applying the load at point A. How will this beam deflect? Like this one? So you mean
Yes,
to
sir.
say,
Yes,
say that the beam will move up from this point also? How come? Can I say that the shape will look like this?
Yes, sir.
Isn't it?
Yes.
When I apply the load at this point, it is connected at this support. It won't move up from this point. It will remain intact at this point, right? And this part will just take an example of a seesaw. It is connected at the middle, and you when one part moves up, the other one moves down, and at this support, it remains intact, right? So you need to visually see to plot the deflected shape. You don't have to apply the concept because they may not apply in the case of bending moment, because in bending moment, we don't have this kind of an assumption that the value is 1 at the respective reaction or whatever, right? You need to see it physically, that how the beam will deflect under the action of the load. So this is how the shape will look like for ILD. And I'm just giving you one homework.
सही ये सीसॉ वाली शेप तो तब नहीं बनेगी जब ये दूसरी साइड पे भी अगर कोई लोड एक्ट कर रहा होगा.
Okay, let's say just take a pen in your hand and hold it from this point and apply a unit load at this point, or apply any force at this point. Try to push it upward. What will happen?
कुछ भी नहीं हो रहा.
Huh?
कुछ भी नहीं हो रहा सर.
Why? You are holding this pen from this end and applying the load. If I have simple pen, it will move up from this direction, right? If you apply a force at this point,
Yes sir.
it will move up from this point, right?
Yes.
And what is happening at the other point? Is it going down?
Yes sir.
So this is what this shape look like. So this is what the deflection is. At this point, it can't move up because the purpose of this support is to resist the vertical movement. What does the roller support resist? The vertical reaction only. So it won't move up at this. You got the idea?
Yes sir.
Are you sure? Because
Yes.
this is what we have to do in every problem, and if you do this wrong, the whole question won't have any points or significance or whatever you can call it. All right. So let's move on to how to plot the ILD or the steps for shear force. For example, I have the same beam and I want to plot, and just note down, this is not in the slide, but I'm giving you one homework to plot the ILD for this beam or ILD for reaction at A using tabulation method. So after you do this, you will see that you are going to get the same shape as we have got by implying the concept of deflection. So do it by using tabulation. It's not that it's just a concept, it's same as the previous one. So in this case, if I want to plot the ILD for shear force at point P, which is this one, what will I do? I will simply divide the beam into two sections. I will apply a roller guide here, again, just like we did in the case of reaction, and I will apply the shear force on the left side in the downward direction and on the right side in the upward direction. Okay, so how will my beam deflect? How will this part deflect? Will it move up or will it move down?
Downwards.
It will move downwards, right? And what about this one?
Upwards.
Upwards, like this?
Yes.
Yes?
Yes, sir.
Oh, sir.
No,
How?
sir.
How?
सर रोलर पे 0 होगा सर
Right.
और एंड पे नेगेटिव में होगा.
Right. Just like this question. It's the same one. So try to get this idea, and if you have any confusion, just ask me right now. Don't get confused later on. So this is my ILD for shear force at point P. So there are three steps basically. I need to cut the beam into two parts at this point or the point under consideration. I have to apply the roller guide, and I will apply the shear force downward on the left side and upward on the right side. And I will plot the deflected shape, and that deflected shape is the qualitative ILD for shear force at P. You got the idea? If there is no question, I assume that you have understood everything. And I will be giving you one question now. Or first, let's discuss it for the bending moment. Let's say I have to plot the ILD for bending moment at point P. Or wait, my beam. So what are the steps? The first step is I have to cut this beam into two sections, right? And now I have to apply an internal hinge, just like we showed the roller guide on which cannot resist the vertical loads basically. So in this case, I will show an internal hinge at this point, which the purpose is that it cannot resist the bending moment. Okay, can't resist bending moment. So it cannot resist the bending moment, and I will apply two moments. On the left side in the counterclockwise direction, on the right side in the clockwise. In all type of questions, just follow this same sign convention. Okay, and then I have to note down the deflection of this beam. Now what will happen to this point if I try to hold it from here and rotate it in the counterclockwise? What will happen? This will move up, right? Anyone?
Yes, sir.
And what will happen to this part?
It will move upwards as well.
But it will pass through the support because support won't allow it to move upward, right? Just like in this example, the same concept. So this shape that I have shown you in the green is equal to, is my bending moment, not just this part, the whole shape. Is the bending is the ILD for bending moment at point P. So I have to look at it visually and I have to see how will the beam deflect. And if I have figured it out correctly, I will get the shape of ILD. If I can't figure out directly, I again have to go back to the method of tabulation or equation to get the correct shape. So try to learn this concept. I will be giving you some example problems so you can have.
Sir,
Yes?
ये roller support moment को तो resist नहीं करता ना?
This roller support?
Yes. तो
just try to visualize what will happen when I apply the movement at this point. It will try to move up basically. If it okay, let's say you are saying that it will go on like this. Do you think that it will happen in actual conditions? That if you hold one beam from this point and apply a movement at this point, will it move up?
No.
No?
Okay, sir.
So this is how you get the shape. Okay, let me give you another question. Let's say I have this beam and I want to plot the ILD for shear force at P. So what will I do? I will divide this beam and this is point P basically. Divide this beam into two parts. I will apply a roller guide over here. Downward shear force on the left side and upward shear force on the right side. So what will happen in this part? This will just deflect like the example of seesaw. And what will happen with this one? It is the same case for this one. It will deflect something like this one. And if I connect all these points, I will get the shape of influence line diagram. Basically the deflected shape, but this shape is equal to the ILD. So you got this concept, right? Now let me give you one question, and this is the last one in this lecture. Then we can conclude our lecture. let's say I have this beam and I want to plot this is my point P, and at this point I want to plot the ILD for shear force. So can anyone tell me how will the shape look like? Anyone, just do it on your paper in 1 or 2 minutes. Just do it.
So at point P?
What?
At point P, sir?
ILD for shear force at point P. P.
सर राइट साइड पे सीसॉ बनेगा जिसका पिवट जो है सपोर्ट पे होगा लेफ्ट वाली.
Daniel, have you done it
Yes.
on the paper?
Sir, I am currently engaged in doing it, but all I can assume is this much.
Okay, just show me.
Sir, I have no source to show you.
You don't
Sir,
have camera.
Sir, it's not functional.
Okay, just physically see that you are saying that on the right side there will be a seesaw. How will that seesaw look like?
Sir, it will be pivoted on the left support. पहले तो
Like
सर हम इस डायरेक्शंस ड्रॉ कर लेंगे ना इसको जी ऐसे. मतलब
and
हमें
here,
पता है स्प्लिट कर रहे हैं जी
What?
ऐसे. सर और जो पी की जो लेफ्ट साइड है ना वहां से डिक्लाइन कर रही होगी एक लाइन.
like this?
सर ऊपर से टॉप से. नहीं ठीक है.
Okay. Anyone else? Daniel, try to look at it again.
सर अगर आप अपवर्ड रिएक्शन फोर्स अप्लाई करें पॉइंट पी के लेफ्ट साइड से तो वो उसके पी के जो बिल्कुल राइट पे जो पिवट है उससे क्रॉस करेगा और उधर ही जहाँ से दानियाल ने बोला था जहाँ वहाँ पे एंड करेगा नीचे लेफ्ट राइट साइड पर राइट मोस्ट वाले पिवट पे और वो लेफ्ट सबसे लेफ्ट से आप यहाँ से वो कर दें आगे ले जाएं सर लाइन और हाँ यस यहाँ पे एंड होगा.
Okay. Anyone else?
सर सीसॉ नहीं होगा.
नहीं बनेगा.
What?
सीसॉ नहीं बनेगा क्योंकि वो हिंज सपोर्ट है. फिक्स सपोर्ट है. नो हिंज सपोर्ट है.
Yes. So what will it look like? There will be some kind of a
तो
shape.
यहाँ पे नहीं होगा मतलब क्योंकि ये दो पॉइंट्स है जहाँ से बीम अटैच्ड है तो अगर हम इन दो पॉइंट्स को रखें तो वो फोर्स लगाने से वो नहीं मूव होता.
Exactly. That's the correct answer basically. So you don't have to look at any concept for this one. Let me show you. First, we need to just do our simple steps. Apply a roller guide over here and the downward reaction or the downward force in this direction and the upward force in this one. What will happen on this side? This side won't move anywhere because this support won't allow it to move and this support won't allow it to move. So keep applying the force at this point and you will see that it won't go anywhere, right? What will happen to this part? Because now we have divided the beam into two parts, right?
Yes, sir.
So what will happen to this one? I apply the force at this point. What will happen?
Sir, this will move because there is no support.
It will move down.
Yes, sir.
Or it will simply fall away. So what is the deflection? This one. So this is basically the ILD for shear force at P point. Only this shape. And this is for the whole beam. This part this section won't be going anywhere and this part will move down simply. So any confusion about this?
सर P वाले point पे सिर्फ क्यों नहीं सीसॉ बन रहा?
Here?
हाँ जी यहाँ से
Like this?
जो रोल जी.
Let me again show you. What we do for plotting the shear force. We divide the beam into two sections, right?
Yes, sir.
And basically, actually just ignore this. We apply an upward force on this one and a downward force on this one. Okay, so now there is no P point where that is connected. There is a roller guide actually over here. Okay, so now they are not connected. Let's just say it like that. So what will happen on this side of the beam? Nothing will happen. It won't go anywhere. And what will happen on this point? It will move down. and there will be a seesaw on P point if they were connected, but now they are no more connected.
सर
Right?
वो तो सपोर्ट्स तक कुछ नहीं हो रहा है, या फिर पूरी ये जो लेफ्ट राइट साइड वाली पूरी बीम है उसके अंदर कुछ नहीं हो रहा है, या दोनों सपोर्ट्स के बीच में कुछ नहीं हो रहा?
On this whole side, for example, if I give you this question, the final thing will be something like this. On the whole side, nothing is happening. On the right side of P, there won't be anything. If this is my P point, this is my ILD for point P. ILD for shear force at point P. And on this side, it will be 0. And now if you solve it by the method of tabulation or by using the equation, just I encourage you to solve it. Let's say just assume the length as 2 meter and this is like 3 meter, and solve it by the method of tabulation or equation. You will get only this shape for the ILD. And you have to look at it visually. You apply the load at this point, this won't go anywhere, right? And this will move down simply. And you connect all these and you will get this shape. Any confusion?
और सर ये ट्रायंगुलर क्यों नहीं है, मतलब फ्री एंड पे?
Just have a pen in your hand and there is no support in it, and I will apply the load, and what will happen? It will fall down, right?
Yes, sir.
It will, right?
Yes, sir.
सर ये मतलब सारा का सारा जो है ना सेल्फ अज्यूम्ड होता है, इसमें कोई कैलकुलेशन नहीं है जैसे?
Not self-assumed. It actually happens in the physical. If you do it for any case, it is a real thing. Actually, based on these kind of physical phenomena, we make all our equations and everything.
So ये shear force का एरिया है, ये pivot तक extend क्यों नहीं होगा?
What?
अच्छा नहीं, असर force हमें point P पे apply हो रही है ना?
Yes.
तो इसलिए हमारा shear force सारा left side की तरफ extend हुआ है सिर्फ, shear force का एरिया जो है.
This one.
हाँ जी सर.
Okay. Look at this beam, Alian. There are two forces. Actually, shear force is the equal and opposite forces acting on the face of the beam. So on the right side, this force is acting, and on the left side, so let's say now we have two beams. One is this one is this one. So on the right side, this shear force is acting. So it will try to move it up. But due to this support, this beam won't go anywhere. Only on the left side, we will have some kind of a deflection.
बिल्कुल sir.
Yes, so this is.
Thank you, sir.
Now we have the same beam and plot the ILD for bending moment at the same point. How will it look like?
Triangular.
How come? Like this? Anyone? Snan, was that you?
Yes, sir.
So tell me, how will it look like?
Sir, इसी तरह triangle बनेगा.
On which side?
Right side.
Right
Left,
side.
sorry. Left side.
Okay. What will I do? I apply an internal hinge on this side and I will try to rotate this part. What will happen? I will get this triangle.
It will move upward.
What?
It will move upward.
Actually, it is moving downward.
How?
Just think about it. I will tell you in a moment. So anyone have any confusion about this one? Or all others have got this idea?
नहीं सर, ये नहीं समझ आई.
Let's say I have this beam and I want to plot the deflected shape due to bending moment at point P. What will I do? I will cut this beam into two parts at P point and I will apply this type of bending moment at this P point. So what will happen on the right side? First, let's figure it out. Let's say I will hold this beam from this point and try to rotate it in the clockwise direction. Will this beam move?
No, sir.
No, it won't, right? So now again, I will hold this beam from this point and apply counterclockwise movement. What will happen? This part, or from here, it will start moving downward, right? I'm trying to rotate it in this direction. It will start moving in the downward direction because I am holding it from this point. And what will be the final shape? This inclined shape, right? Just take a pen in your hand and try to rotate it in the clockwise direction. It will move in the triangular direction or the inclined direction, right? Any confusion?
सर लेकिन जब हम इसे यहाँ से रोटेट कर रहे हैं तो दूसरी साइड नीचे आ रही है ना, मतलब जो आपका बिल्कुल एंड पॉइंट है
Yes, this one.
तो ये नीचे आ रहा है ना, इस तरह
Yes.
स्ट्रेट तो नहीं आ रहा.
No. Okay. Let's say the final shape will look like this. You are saying this, right?
सर मैं ये कह रही हूँ कि ये मतलब जो पॉइंट पी है उसके नीचे स्ट्रेट लाइन नहीं होनी चाहिए.
Point P. I don't get it. Can you show me how you plotted, if it's possible for you? Yeah,
सर देखिए मैं ये कह रही हूँ कि जब आप एक पेन को एक साइड से पकड़ रहे हैं, लाइक लेट दैट
Yes.
बी पॉइंट
Yes.
पी, तो
Yes,
फिर
yes.
तब आप उसे मूव करो तो फिर वो सीधा तो नहीं जा रहा, मतलब दूसरे एंड से वो बिल्कुल एकदम से नीचे तो नहीं जा रहा, तो ये कैसे शेप बन रही है?
No. Okay. For example, you are holding this in this one. So you try to rotate it. What will happen? This part is moving up and this part is moving down. So what will be my final shape is? It is basically an inclined shape. But it is not passing, it won't be like this because it is not passing. This is my final shape of this whole beam. And this is what my deflected shape will look like, right?
सर ये डिफ्लेक्टेड शेप, ये देखें ये ऊपर भी तो हो सकता है, जैसे मतलब P के ऊपर ग्रेटेस्ट वैल्यू और ये वाला लोएस्ट.
Actually, yeah, I get your point. Actually, you know what happens when you apply a movement, and that's why I said that you need to hold this point, because movement, in the case of movement, you need to apply the rotation. You are applying the rotation basically. Let's say that this point won't be moving up. This point is now in your hand and it is being pivoted, and this point won't be going anywhere. This is how you apply the rotation. You have to hold it. So you hold this point and try to move it up. So basically, in the counterclockwise direction, the movement is somewhere acting over here when you are rotating. So what will happen? This point is the pivot point. It will remain as it is, and this part will be moving downwards. Now, did you get it?
Yes.
So it happens in the case of movement. Even if you see in the case of, for example, if you have some like a string in your hand, and when you are rotating, one point is pivoted point which you are holding, and you are rotating it in the clockwise direction. So the rotational motion is taking place around one point only. That point is a fixed point. So that is a good example to understand it, right? If this point start moving upward, that means that this is not a pivot point, and this will be same as a vertical or the upward force acting at this point. So this point needs to be fixed. Okay.
सर तो इस तरह जो पिछली एग्जांपल्स हमने किए उसमें फिक्स क्यों नहीं रखा हमने? उसमें तो यहाँ पे ट्रायंगुलर शेप इसीलिए बन रही थी क्योंकि हाईएस्ट हमने उसी पॉइंट पे लिया था.
Wait. Where is it? Yeah. Now look at this. Yeah. I get it. Now look at this one. So what will happen? This point is not going to move up. Okay, this point is a fixed point. Okay, so what will happen? I keep on applying the force at this point, but this point won't go anywhere. So what will happen at the end when the force will keep on increasing, that this point will start moving upwards. I keep on applying the moment. This point is not going anywhere because this is fixed at this point. And then finally this point, this part will go up. But in this case, let's see. I will apply the force, but there is no support at this point. So immediately this point will move downwards, and this will be the deflected shape. And actually this happens in the case of real phenomena. The deflected shape, the moment the beam is deflected, like if you get this much deflection, immediately the beam will fail and the structure will fail basically. So this is the whole concept. And in the calculation, you then take these deflections. You don't have to think about later on that this will go in this direction, because I will keep on applying the moment and the beam may go over there, and it will go, it will revolve in 360 direction. But what is the immediate deflection? Immediate one is this one. I will hold this point and apply this one. But in this example, you keep on applying the force, this won't go anywhere. But finally, when I will keep on applying the force, this part will move up. Did you get the idea?
Yes, sir.
Okay. Yeah, I forgot to mention this point in the previous one. Thank you for reminding me. So any other question? Nothing. So if actually this concept is new one, so I would suggest you to solve these questions, and I will try to send you this whiteboard that we have did for today, if it is possible. I don't know yet if it's possible or not. So if it's possible, I will send you this whiteboard also and try to solve all these questions that I have given you. I will also be giving you the assignment for ILD because this is very important concept. And for now, your homework is try to solve 1 or 2 questions, especially these last 2 questions, by using the method of tabulation or equation, and see that whether you get the same shape or not. If not, then we can discuss about it again. So solve these by method of tabulation and equation. And I will be giving you the assignment, and the assignment that you need to submit for now.
सर आपकी आवाज़ नहीं आ रही.
Someone did it. Okay. So you need to solve the assignment 4 and you need to submit it by next Thursday. Okay. And solve these questions by method of tabulation and by using the equation. So this concludes our lecture. Thank you very much for your time, and we will meet for this course in next week. And we will be having the lecture of mechanics tomorrow, and I will inform the time in the groups. Okay. Thank you. Take care. And if you have any question, just send me a message about these questions. Allah Hafiz.